Hello. Now, today we are going to be doing something called differentiation by rule. We already know differentiation by first principles. And when we did differentiation by first principles, there's a pattern that emerges when we do it. If we start out with a function that would be, say, y is equal to x to the power of n, so f of x would be x to the power of n, when we differentiated it by first principles, in practice, we ended up multiplying by the power and subtracting one away from the power. So say if we started out with y is equal to x cubed. We started out with the function y is equal to x cubed. When we got dy dx, or when we got f dash x, in practice we ended up multiplying by the 3 by the power and then subtracting one away from the power. So we ended up with our dy dx, or our f dash x, being 3x squared. Now, because this pattern, as it turns out, works out all the time, we wrote it down as a rule. So this is differentiation by rule. It's using this rule here, which is on page 25 in your log tables. So this is a rule that it comes out of recognizing a pattern from when we do differentiation from first principles. That's where it's come from in practice. When we want to do differentiation, we are going to open up page 25, and there are going to be several different rules that we're going to need on page 25 when we're doing differentiation type questions. And it's important to keep linking back in with them because there are quite a few of them and we need to be very clear on them. So this is what the pattern is. A general note here, you can see that we're using the power on the x as the key thing we're using. Write absolutely everything you're given in a question in power notation. Now, I'm going to remind you of exactly what that means in a minute, but make sure that's clear for yourself. Differentiation is done when everything is written in power notation, where we have x to the power of something. Now, another note that we need to keep in mind is that the derivative, the dy dx, or the slope of a constant, would be equal to 0. Now, I've given you a quick sketch to give you an argument as to why that would be. Say we had a constant y was equal to 2. What would that look like if we drew a picture of it? Well, we'd have a horizontal line with y just equal to 2. What would be the slope of that dashed line? It would be 0. The slope of a horizontal line would be 0. Therefore, dy dx for a constant would be equal to 0. So if you can keep that visual image in your head, great. But in general, if you get dy dx or f dash x of a constant, which is to say just a number, something not involving x, then it's going to be equal to 0. So when we do the derivative here of minus 1, it's just going to end up being 0. So let's put this into practice here with our function y is equal to 3x squared plus 7x minus 1. So dy dx we are going to multiply by the power. So we're going to have 2 on 3x. Multiply by the power, so 2 is the power, so we multiply by the power, and subtract 1 away from the power. Here we have x to the power of 1, so it's going to be 1 on 7 to the power of x and 1 minus 1. And then we have 0 here. So our constant term, its derivative is just 0 for the reason I just gave you here. Now, we want to simplify this down a little bit, and we get 6x to the power of 1 plus 7x to the power of 0. 7x to the power of 0, x to the power of 0 is just 1. So we end up with 6x plus 7. Now that is the slope function for that quadratic. This equation, dy dx, is equal to 6x plus 7, gives us the slope of this curve for different values of x. So I'm going to switch to GeoGebra for a second. This is the curve here. This is our quadratic that we're dealing with. And our tangent line, here, this is the slope of that tangent line. So this is the slope of the tangent to the curve. Sorry, this is the tangent line, and this is the slope of the tangent line to the curve at different values of x. If I change my value of x, so I change where b is on my curve, I can see that the slope of my line is changing. Here, the slope of the tangent is negative. It's minus 5.7. As I change x, I can see that the slope is becoming closer and closer to 0. And it becomes 0 around here. And then it becomes positive. The slope of my tangent line now is 1 at this point. It's becoming more and more positive as I go on up in the x values. So my slope is changing. This number here is my slope, and that is coming from this equation here. So if I put in a particular value for x into this equation, it gives me the slope of that tangent line. That's what dy dx gives me. It's the slope of the tangent to the curve. Now, that was a fairly straightforward use of our rule. Let's go for one that's a little bit more mathematically messy. So I have f of x is equal to 3 all over x squared plus root x. First job, turn this into power notation. So I have an x underneath the line here. To turn it into power notation, it should be on the top of the line. So if I move up a term onto the top of the line where it was below, I change the sign of that term. So this is 3 multiplied by x to the power of minus 2 plus root x, square root of x means x to the power of a half. Always we must turn our functions into power notation like this before we do our differentiation by rule. So now this is my function. Now I am going to get the derivative of that function, so I'm going to use my rules from page 25. So I'm going to multiply by my power and subtract 1 away from my power, plus multiply by my power, subtract 1 away from my power. So I have x to the power of a half minus 1. That becomes minus 6 x to the power of minus 3 plus x to the power of minus a half all over 2. And simplifying that down further, I'd have minus 6 all over x to the power of 3 plus, I have a minus power here and a minus power here, so they're both going to go underneath the line. 1 all over 2 to the power of, 2 by root x. So that is my derivative. Now I haven't bothered drawing this function because it looks very odd, and it doesn't. We don't need to worry about it. The key thing for this example is we need to write the function in power form, and then we are going to be able to use our rules, and at the end we should simplify down again. Now let's have a look at an example where we can talk about the tangent more directly. So we have y is equal to x squared plus 1. We want to find the slope of the tangent to the curve at x is equal to 3, and therefore find the equation of the tangent to the curve at x is equal to 3. Now, I have y is equal to x squared plus 1. I want to find the slope of the tangent to the curve at x is equal to 3. That means I am looking for dy dx. That is the name for the slope of the tangent to the curve. Slope of the tangent to the curve is dy dx. And I want that at x is equal to 3. And then I'm going to find the equation of the tangent. Well, I'm going to do the first part of the question first. I recognize that this sentence means get dy dx or f dash x. So I have dy dx here. I have y here, I should say. Dy dx is going to be using our power rule. So multiply by the power and subtract 1 away from the power. And the derivative of a constant is just 0. So that becomes 2x. The slope function, or the slope of the tangent to the curve, is just 2x for our quadratic here. Now, that is our first part of our question almost done, but we need to find out what that's equal to when x is equal to 3. So dy dx at x is equal to 3. You can put a line down and say at x is equal to 3. It's a shorthand way of saying at x equals to 3 is going to be 2 by 3 is 6. So the slope of the tangent line to the curve at x is equal to 3 is going to be 6. And now we want to find the equation of the tangent line. Well, we know when we hear the word equation of a tangent is a line. So I'm going to write down my formula for a line and see what information I need. Well, I have the slope now. That was dy dx at x is equal to 3. At x is equal to 3. And that was just equal to 6, what I just found. But my point, what's my point going to be? Well, I know that x is equal to 3, so I know that my x1 coordinate is going to be 3, but I don't know what my y is. But I can find it because I know that y is equal to x squared plus 1. This is just a normal function. So let's find out our other point. Y is equal to x squared plus 1, and we have x is equal to 3. So we have y is equal to 3 squared plus 1, y is equal to 10, so our point is going to be 3, 10. So we sub into our equation, y minus y1 is equal to m on x minus x1, x1, y1, and my slope is my dy dx is 6. So y minus 3 is equal to 6 on x minus, minus 10. 3. So I get y minus 10 is equal to 6x minus 18. Y is equal to 6x minus 8. So this should be the equation of the tangent to the curve at the point x is equal to 3. So let's go to GeoGebra and double check whether that's correct. So when we go to GeoGebra, we have our slope of our tangent. We have our tangent line, I should say, going to our curve. This is our quadratic curve. This is our tangent, and we can see that the equation of that tangent is y is equal to 6x minus 8. And again, that is the slope of that is the tangent to our curve at x is equal to 3, and we can see that graphically that works out the same. So